Hello everyone, welcome to our project presentation on microcontroller-based digital overvoltage protection system for industrial loads. We, the member of group B15, will demonstrate this presentation. Here is the outline of our project presentation. Our project is mainly focused on overvoltage protection of industrial equipments for a three-phase power system, and we have designed a microcontroller-based system to minimize the damage of industrial equipments in an overvoltage condition. The automation and the development of industrial electrical power systems has also introduced the requirement for their improved reliability and efficiency. So, careful attention has to be given to protect electronic components of industrial equipments and ensure a safe shutdown in case of emergency. A high voltage stripping mechanism is used for industry graded overvoltage protection circuit. This protection circuit is able to distinguish between normal voltage fluctuations and harmful overvoltage. In a standard protection circuit, the main AC power supplies the power to the whole circuit, and for operating loads by using relays, and also for tripping the loads in presence of the input voltage which falls above a set value.
Now I would like to explain how we have designed our algorithm to implement this overvoltage protection. First, we will measure the all three-phase voltage of the source. Then we will compare each three-phase voltage with a predefined threshold voltage value. In our project, we consider 220 volt as nominal phase voltage. Anything above 250 volt will be considered as in overvoltage condition. If an overvoltage situation occurs for any phase, we will observe this particular phase voltage for 10 seconds to check if it is still high. The motivation behind this is that the system does not give any false alarm for any random short high voltage occurrence. If the phase voltage is still high after 10 seconds, we will decouple the load from the main source voltage. Now I will discuss the circuit sensor components. Here are the main circuit sensor components in our project. There are Arduino Uno for the microcontroller unit, relay block to isolate load from the source, and voltage sensor block to pass process voltage value to the microcontroller. I will describe each block function in details in the next slides. For the microcontroller unit, we use Arduino Uno. Here, port A0, A1, A2 are the input pins for the microcontroller. Through these pins, it reads the phase voltage. Comparing this voltage with threshold voltage, a signal is given through the gate signal through port A. This gate signal goes to the relay block to isolate the load. There is one more port A3 to restart the circuit operation again. The operation of this port A3 is demonstrated later in this presentation. Here is the relay block. This is the main block to protect the load. When the gate signal is low, the relay is in close contact and the circuit operates. But when there is a high gate signal, the NPN transistor turns on. Then there is a path to energize the relay. The energized relay creates an open path in the main circuit and the loads get isolated. For three phase, we design the block with three relays. Here is our voltage sensor block. It is not safe to use the direct voltage value from the source to give input to the microcontroller, as high voltage can damage the microcontroller. That's why we design a voltage sensor. It is basically a negative comparator which compare the step down voltage with 5 volts and give input to the microcontroller.
For our design, we used an ideal three-phase source as our voltage source, as it can be seen from the schematic. The three phases are connected to the three loads, and the loads are controlled by the relay system. After that, we designed our voltage step-down and rectification system to convert the higher source voltage to a lower voltage so that it is safe for the voltage sensor to read the signals. We converted a high 220 volts to a low voltage of around 5 volts. The step-down circuit was implemented using simple op-amp components. The voltage was then rectified using a full bridge rectifier to get rid of the AC components. The signal is then sent to the voltage sensor. Now let us look at our simulation here. In our simulation, we can see that the design contains all the components for our voltage protection system as mentioned earlier. Our system will trigger the relay if any of the three phases as shown here are in overvoltage condition. After an overvoltage condition has been taken care of and all the phase voltages are in the safety region, the relay needs to be manually turned off by this switch here for the system to work again. This is done to ensure that the whole situation is under control before current flows to the loads again. Now let us simulate our system. As it can be seen from here that all the phases of our source are in the safety region of around 220 volts. Now, if phase A goes to overvoltage condition as shown here, we will see that after some time period, the loads will disconnect from the source and they will turn off. As you can see here that all our loads have disconnected from the source. Now, if we turn back our phase A to a safety margin of around 220 volts as shown here, now we can still see that the loads are still disconnected and no current is flowing through them. Well, we have to manually disconnect the relay using this button here, and if we, after pressing that button, we can see that our loads are again conducting current. For our system, we designed a PCB that shows all the components as seen here. We used Proteus auto routing to connect the components, and the layout was verified by the standard design rules. We also designed a 3D visualizer for our PCB circuit.
So far, we have seen the implementation of project with Arduino. Here, an additional circuit is designed with 8086 microprocessor for overvoltage protection. The 8086 is used to read the voltage values from 8255 and programs the device to get disconnected when the voltage is over the threshold value. The 8255 acts as the programmable peripheral interface to read the voltage values from ADC converter. As 8086 does not have an internal ADC converter, the ADC 0804 is used to convert the analog values of voltage to digital values and feed it to 8255. As microprocessors operate with DC voltage, the source voltage is stepped down and rectified. Here is the PCB layout and the 3D rendering of the circuit designed. This is the circuit designed with 8086 for overvoltage protection. First, in the code, here the address of 8255 ports have been defined. Then the control word, which initializes port A as inputs and port B and port C as outputs, was sent to the control register. Here, the comparison was done to see if the voltage exceeds the threshold of 224 volt. If the voltage does not exceed the threshold, then it displays the value in port C and allows the circuit to operate in normal condition. If the voltage threshold is exceeded, then the relay is energized and the circuit is disconnected. If we run the simulation, here we can see the circuit is operating under normal voltage condition and the values are being shown here. However, if we increase it to a certain threshold, we can see the circuit has been disconnected, and the value at which it has been disconnected is shown here in the port C. The system could have been made more efficient by using improved voltage sensors and better step-down and rectification scheme. Moreover, it could have been implemented with GSM modules to communicate with control room, making it a smart system. To conclude, the system was designed with relays which operate instantly, making the system more reliable. The project could be made more versatile by introducing the undervoltage protection scheme. Manual re-establishment of connection ensures that the circuit does not start operating again before making sure of the proper conditions. With this, we conclude our presentation. Thank you all.